Hi, everybody. So today what we're going to be doing is looking at lesson 3-1, and we're going to start getting into geometric reasoning and two-column proofs. Okay, so this is the start of all of our proofs here. So make sure today you have your Springboard book, pen or pencil, and a highlighter. And let's get started. Okay, so at first I want to start with this little dilemma, called a dictionary dilemma. So, have you ever looked up a word in the dictionary only to encounter another word you didn't know? So then when you go to look up that word, you find that it's defined using the first word that you even went to look up. Okay? So this causes you to have a vicious cycle. Okay? You're trying to define a word, you try to look it up, but it's using other words that you don't know. Okay? So then you're looking at more words. So in geometry, we see this a little bit because geometry is an axiomatic system. Okay? And what that means is from a small basic set of agreed upon assumptions, an entire structure of logic is devised. AKA meaning most of geometry is based on a set of simple principles and they build the entire curriculum or ideas of geometry off of that. Okay? So I'm going to get into this little example that they have here where we compare the following definitions. So the first word is a fountain. So according to your book, a fountain is defined as a roundel that is berry waxy of 6 argent and azure. So when you're reading that or listening to me read that, I'm sure you're thinking, what are they talking about? Okay, when I think of a fountain, I think of this, okay? Something that sprays water and is pretty to look at, right? Well, compare that to this word, a gauge, which I don't actually know what that is, but the definition says it's a belt that is worn over the right shoulder and used to support a shield. Something like this. Okay? So which of these is easier to understand? I would think that this, the gauge, I could figure out what that is based on the definition because I know what a shoulder is, I know that it's a belt, I know what that is, I know what a shield is. So based on some clues in the definition, I could figure out what they're talking about. That definition of a fountain, I would have no idea what they're talking about based on that. Okay? So geometry is thought of using the same thing. Okay? So all geometry is built on these, what they call the fundamental undefined terms, okay, of geometry. And those 3 terms are point, line, and plane. Okay? So every definition that we know in geometry or that we're learning or going to find out or going to learn are based on these 3 definitions. Okay? A point, a line, and a plane. So that's from our first lesson we defined those terms. Okay? So if I look at some of these words here that they have for us, which we have already defined most of these. But remember, a ray we defined as part of a line bounded by one endpoint. Okay? Or, it looked like this. Okay? A line that had one endpoint and one stopping point, right? Collinear points. Okay, well, those are all points that lie on the same line. So, for example, if I draw a picture, we have, let's say, 3 points here. They're collinear if they're all on one line together. And I'm sure you can assume what a coplanar point is. Okay, those are points that all lie in the same plane. So if I have a plane, let me just draw one real quick. And we have, let's say, 3 points in there. Those points would be considered coplanar because they're all on the same plane. Okay, so looking at these definitions, you can see that they're all kind of structured around our 3 undefined terms, point, line, and plane. So a ray is a part of a line bounded by one endpoint. Okay, collinear points are points that are on the same line. Coplanar points are points that lie on the same plane. Okay, so every definition that we learn in geometry is going to be based off of these kind of 3 undefined terms. Okay, since once we know these 3 terms, we can use it to define more terms. Okay, and we keep building on it to kind of create more definitions and things that we know in geometry. Okay, so we can also apply this to an angle. Okay, because it says an angle is defined as a figure formed by two rays. Well, on the first page, I was able to define a ray based on a point and a line. Okay, so you can see here we're building. We started with a point and a line to give us a ray. Once we know what a ray is, we can define an angle. Once we know what angles are, we can get that we know what complementary angles are. Okay, they add to 90 degrees. Similarly with supplementary angles. Okay, so the point that your book is trying to get at here is just every definition builds off of prior knowledge in geometry, and that prior knowledge comes from those three main definitions: point, line, and plane. All right, so we're going to start here and getting into some proofs. So we're going to use the process of deductive reasoning, okay, which we know is proving something without a shadow of a doubt. So there's no interpretation, okay? It's either right or wrong, and we know it's true using deductive reasoning. So a conclusion based on deductive reasoning cannot be made unless there is an established assertion to work from, aka we need to prove it, okay, using logical reasons and systems in place. So we're going to start with something you may remember from algebra, solving equations. And we're going to actually prove why we can solve this equation, right? So I have this equation, 4x plus 9 is equal to 18 minus 1/2 x. Okay? So the reason we're able to prove things is because we have different properties in place in mathematics. So there's a whole list of them in this connection to algebra. But they're always going to start by giving you some information. So we would call this our given. Okay, they told us what the equation was. Okay, and now there's a couple ways that we can go about solving this, but I'm just going to start by putting all my variables on one side. So say I add this 1/2 x over. That's going to give me 4.5 x, and then plus 9 equal to 18. Well, why was I able to add that over? Well, it's because we have a property, and it's right over here. Okay, we have this addition property of equality, which says if you add something to one side, you have to add it to the other side. So this is our addition property of equality. I'm going to abbreviate there a little bit, but okay. So then if I continue to solve this, what would I do next? I probably would move this constant over and subtract 9. So we get 4.5 x is equal to 9, because 18 minus 9 is 9. Now, why was I able to do that? Because we have a subtraction property of equality that allows us to, if we subtract something from one side, we can subtract from the other. Okay? And lastly, to get x by itself, I would just have to divide out this 4.5. Okay? And if you did your work, you would get that final answer that x equals 2. And again, why was I able to divide on both sides? Because we have a division property of equality. So again, we're not just solving things because we're saying, oh, we can do this. There's a reason, okay? There's deductive thinking process going on here where we're using actual properties, okay, to go ahead and solve equations. So x equals 2, okay? So let's try a couple more in your book here. So you can organize your steps and reasons used to justify the steps in 2 columns with statements, which are our steps, on the left, and the reasons, the properties, okay, on the right. This is called a 2-column proof, and we are going to be doing a lot of these in geometry, so they won't go away anytime soon. But they're saying your steps are on the left here, and your reasons, okay, your deductive reasons, okay, that are proved by actual properties are on the right, okay? So we'll just go through this one quickly from your book, but let's look at problem 1. Now, there's different ways to solve the problem, okay? Your book's going to, okay, it might solve it differently how you would solve it, but it's all the same in the end. But it looks like they started by rewriting the original problem, okay? And we're always going to do that with a proof. We always start with what we are given, okay? Because once we have what we're given, we can kind of base everything else off of that, okay? All right, so next it looks like, well, what did they do? It looks like they moved this 1 to the other side, okay? So it's not here anymore. So it looks like they added it over. And why are we allowed to do that? Because we have our addition property of equality. Okay. Next, it looks like they got rid of those parentheses. So what did they do? They used the distributive property to multiply it through. Okay. Next, looks like they moved that 3x to the right side of the equation by subtracting it on both sides. Okay, then it looks like they moved their constant plus 12 to the other side by subtracting it. Then they divided both sides by 2, and then they got their final answer. Now they're calling this a symmetric property because they just rearranged the order, but there is our proof. So again, we have the steps on why we did something, and then the reasons or the properties behind why we could do it. Okay. So let's do one together here. So they have the steps worked out for us. All we have to do is go in and put our properties in, or our reasons. So there's the original equation. So again, we always start with what is given to us. Okay. Pen a little smaller here. So it's given. Now, this next step, the book did it a little different than I would probably do it, but we can see that they're multiplying something on both sides in an effort to kind of clear out this fraction. So what our operation they're doing, they're going to be multiplying. So this is our multiplication property, right? Okay. And it looks like they simplified it here. So 2 goes into 10 5 times, right? 5 goes into 10 2 times. So they're calling that their substitution property. And again, all these properties are listed on the page before it. I just can't show it on my screen at the moment. But they're substituting or simplifying 10 divided by 2. You're substituting that in with the number 5 instead. Okay. All right, what did they do next? Looks like they distributed. So that's our distributed property. Pen keeps going out a little bit. Okay. Next, let's see what they did. Looks like they moved their 2x's to one side. So since it's plus 2x, they're going to subtract it on both sides. Their subtraction property. Okay. Next, it looks like they moved that 15 over by adding it. So we have our addition property. And last but not least, they divide by 3 on both sides. So that would be our division property. Okay. So again, every time we're making a proof, we're going through and just putting in the reasons or the properties about why we can do a certain thing in math. Okay. So I'm going to have you try B. You're going to make a 2-column proof for that equation in number 4. Number each statement and corresponding reasons. So you're going to do exactly what your book does here, where you have the statement as 1 and the reason as number 1. Okay, 2, 2, so line them up. So I'm going to have you guys try that on your own. Okay, I just want to finish up here with the check your understanding. So let's think about why undefined terms are necessary in geometry. So take a minute there and think about that and why you think they are necessary. Okay, so like I pointed out a few times in the beginning of the video, all of our vocabulary is built off of those 3 terms. Okay, once we know what a point, line, and a plane are, we can go ahead and define all other terms in geometry. So that's why they're very important. Point, line, plane are undefined terms. All right, let's look at 6. What is the relationship between a conjecture, a theorem, and 2-column proofs? So it's kind of combining vocab from activity 2 with our conjectures and our theorems. And how do they relate to 2-column proofs that we just learned about? So take a second and think about that. Okay. Well, remember, a conjecture was just an assumption that we make. Okay. We assume something based on a pattern, so we make a conjecture about it. So we can use these 2-column proofs to actually prove if our conjecture is true or not. Remember, sometimes a conjecture, it works out that it's going to work every time. That pattern will keep continuing. But like we saw in that chords problem in our book, when we assumed the next number would be doubled again, it wasn't actually true. So we're going to use these two-column proofs, okay, with our reasons and properties to prove that a conjecture is true. And once we do that, we form a theorem. Remember, a theorem is something that is proven to be true without a shadow of a doubt. Okay? All right, I'm going to have you guys try number 7 on your own, where Jeffrey wrote a two-column proof to solve the equation 3 times x plus 5 is equal to negative 6x plus 6. In addition to an incorrectly written proof statement, what error did Jeffrey make in his proof and rewrite it to fix the problem for him? Right, so let's go ahead and think through this proof. Where did Jeffrey make a mistake? And then fix it for him. Okay, so he starts with this given, which is good. And then it looks like he distributes, makes sense. He moves that 6x to the other side by adding it. That works. But where we have a problem is right here in our last step. Right? Okay, where we have, when we went from 9x equal to negative 9, he said he used the multiplication property and got this answer, x equals negative 81. Well, we have a problem there, right? Okay, because we didn't use the multiplication property, we should be using the division property of equality. Because in order to undo multiplication, we would have to divide, right? So Jeffrey should have got that x was equal to negative 1 instead, actually. Okay, so make sure you're not trusting these proofs. You actually can back up the reasons and why it's going through them, and make sure you don't fall victim to bad proofs. Okay, so that's everything from lesson 3.1, just introducing two-column proofs. So just make sure all of your reasons make sense and you're using properties to back it up. And always remembering that our undefined terms are point, line, and plane, and they help us make definitions for everything else in geometry.